So for the final, from my understanding, she's using the common final. The common final was put together by all faculty, or all chemistry faculty, and kind of assembled and put together, hitting a couple big targets. So first and foremost, we wanted to make sure the final covered all of the competencies. So you have 28 competencies in this class for some kind of bizarre reason. And if you go back and look at your syllabus, the competencies are all listed out. Okay? Not all competencies are created equal. Okay? So we only get 70 questions, which is how long it is written for. Your instructor may be making adjustments for time, and we can talk about that in a second too. If we just evenly divided up the competencies, that's about 2 questions per competency. Some of those competencies are really important, some of them less so. For instance, your very first competency, and I guess we'll get rid of the doc cam. Your very first competency, not that one. Not that one. That one. What is it? Define chemistry and describe its branches. How important do you think that is? Okay, not too important. It was probably 1 sentence at best stated by your instructor at the very beginning of the semester. Okay, but if we consider conversions, how many conversions have you run throughout the semester? A lot. There's varying context behind those conversions, but they're ultimately all conversions. Stoichiometry, which you guys have been working with, molarity, gas laws, milliliters to liters, grams to pounds, all of those are ultimately conversions, and you've spent a lot of time discussing how to set those up and all of that. Okay, so if we as instructors are trying to build an exam that accurately tests on what we think is important, we're going to put a lot more questions in conversions than we would in define chemistry and describe its main branches. Okay? So the first pass with our chemistry faculty was to send out the competencies and say, rank them. How many questions or how important do you think each of these things are? Okay? And so what we generated by compiling that, some lucky idiot pushed it and got to deal with it, compiled all of those into a number. Those numbers written next to each of those competencies are how important the individual chemistry faculty found those particular competencies. So for instance, define chemistry and describe its main branches. We were required to ask a question about it. As low as we can go is 1. Most people said don't ask a question about it. It's part of our curriculum, we have to. Right? So you will see numbers next to it. Those are the approximate amount of questions per competency. Right? So define chemistry and describe its main branches is only worth 1 question. But if we look a little bit lower, we'll see where some people disagree. Use the unit factor method in solving chemistry-related problems. That's a 4. Right? So we think that is ballpark 4 times more important. Okay? So you'll see more questions on that topic. Okay? The competency right underneath it. Name and write formulas for simple inorganic compounds. 5 questions on that. I think is one of the stupidest competencies ever, and we need to get rid of it, but my opinion only amounts for so much. Okay? And so overarching, that was decided as a big thing. We get 5 questions on that. Okay? Remember, each competency covers a broad area. So if we look at name and write formulas, there's a lot of context that could go behind that. Okay? That could just be classify this formula. What kind of naming rules should you use? Okay? It could also boil down into very complex. Here's the name of a compound. What's its formula? Here's its formula. What's its name? So there's varying levels of difficulty that we can ask within each of those categories. Does that kind of make sense? But this document, hopefully, is the one that you'll get. I don't know if you will. And if she shows you a slightly different one, you can ask her to talk to me, and I'll see if I can't get this one to her so that she can make this one accessible. But she should be making a practice exam accessible. I got that information from somebody. Gianna? You said she is making one accessible?
That's what she said.
Okay. So she should be making one accessible at some point. You might just kind of press on her and say, can we get it sooner if you really want it sooner? I don't think she would object to that, but I don't know. But ideally, this is the one you get. And if you don't, let her know to talk to me, and I'll get this one shipped to her. So this one has all of those listed out. We got all the contents of all those numbers. This table of contents was an admirable idea that turned out to just be stupid. But you could click these and go to individual questions. Okay, so if you did the first 10 questions and you want to skip to question 20, instead of scrolling, heaven forbid, we just click the button and we're there. Okay? That said, you got to scroll a lot to get to the table of contents. And then you get your questions. Okay? They're all multiple choice. I believe the practice exam has 68. So you've got 68 potential practice questions that you could go through and work. The intent behind this practice exam was to match the old common final. The new common final that is targeted to the competencies is more accurate, but the practice exam isn't quite as accurate. So there are gaps within the practice exam. Ultimately, the way the practice exam was written was they were sick of writing the common final, and so they just threw a bunch of questions in the practice exam and just said that's what it was. Right? So the practice exam does have holes in it. So how should you use it? Okay, first and foremost, it's practice. It's not actual questions. So if you go through and do a question within the practice exam and memorize it, that is utterly useless. It's not going to help you. What you need to understand is the content behind the question. So the first one is asking about sig figs and a measurement. Right? You won't see, theoretically, the exact same question. So you don't want to know the answer to the question. You want to know the process by which you get to the answer. Okay? That is very challenging to do, but that should be your target. The next part, what competency does it match or map to? Right? Figure out where it maps, or if it doesn't map, that's potentially not a useful question. Right? For instance, sig figs, it doesn't map, which is an interesting one. Everybody insists that it should be on the common final, but it doesn't map to a competency cleanly. Right? But what you should go through and do as a pass within your practice exam, map each question. Look at it and be like, this is that competency, this is that competency, this is that competency. And build out a grid so you now know what competencies have been covered by the practice exam and which competencies have not been covered. Does that make sense? The competencies that aren't covered, you could then evaluate to the next level. So now you're starting to drill into exam design. Let's say you don't see any questions covering, this isn't going to be the case, but wherever it is, interpret, so which one's a high, where's a number? What was it, 9? You don't see any questions on naming and writing formulas. There's 5 questions on it. It's one of the largest numbers. That means you should go find some practice elsewhere. Where can you find practice elsewhere? Sorry?
I would say Quizlet.
Okay. Never generated anything within Quizlet, but yeah, Quizlet's out there. You could get questions there. Where else could you get questions from? Theoretically, you have a textbook. If you didn't buy one, that's okay. The book or the library has them, and you can open up the chapter on naming, and you could find questions that way. You could look at your old worksheets from class. Does that make sense? Right? So that would be one that you'd be like, dang, the practice exam sucks. It misses a huge gap within it. But if we shift to something else, whoops. Gotta go both directions here. Let's switch to a competency that I know is generally weak. I doubt, though I think I'm actually wrong, you'll see any questions about competency 22. List the factors affecting the rate of a reaction. If you're like, I have no idea what that's talking about, I don't see any questions in it, I don't remember Dr. Grace or Mrs. Grace talking about it, should you go out and find a bunch of questions on this competency? You say, no, why? Why should you ignore this competency? Yeah, look at the number in parentheses next to it. There's 1 question out of 70 on this competency. Okay? You have 0 background knowledge in it. The odds that you are actually going to be able to learn that content on your own to answer that 1 question are slim to none. What does that mean you should do? Accept the loss. You're like, oh, that sucks. I don't want to accept the loss. If you get 69 out of 70 questions, what's your grade? Okay. Versus 70 out of 70? Still an A. Is there a difference? No. Accept the loss. Kind of makes sense? So everybody's going to have to map their own process through preparing a final, and for any exam for that matter. But the final's a little bit cleaner cut because you know exactly what it's covering. You know ballpark question amounts shifting off of that, and you can design your own study process through that. Does that kind of make sense? Oh, yeah? Some head shakes, yeah. You all look really depressed. It's not that early. Okay? If you've got questions, you can talk to the tutors. If you haven't talked to the tutors or aware there's a tutor center, there's a tutor center. You can go talk to them. They'll help you through it. They work these questions over and over and over again. And there are probably more than 6 of them. Right? But they will help. Okay? Questions about the final? Any structuring on that? Like, that's the one thing I can ask about the class, or answer about the class design, is the final. Anything else? Comments, concerns? I'll throw out a comment concern. The practice final is designed for 110 minutes. You don't have 110 minutes. Okay? Which means, what should you do? It's also a hard question. What do you think you should do? You know you are being given a test that has 70 questions on it, and you only have, you're supposed to be done in 110 minutes, and you have 80, 90, however many it is. It's 80? So you have 80 minutes. You're missing 30 minutes of exam time. Y'all happy with that? No? What should you do?
Do the question you know.
Okay, that's one option. As you take the test, it's randomized. Don't start with the first question. Start with the question you know. It's not even the last question. How do you know if you know the answer to the question? You have to read it. So scanning through the whole exam is probably a good idea, okay, before you actually get into the nitty-gritty of it. Because you could very well get sandwiched in dealing with a whole bunch of really hard questions at first. They're hard. We're likely to get them wrong anyway. Move on to those easier questions. Okay? So testing strategy, that's useful. There's a better one. You've got 80 minutes to complete a 110-minute exam. You're missing 30 minutes, and you're just going to sit down and take it. Seriously. You're just going to accept it. Don't accept it. Ask. Talk to your instructor. Be like, aren't we supposed to get 110 minutes for this thing? She'll probably be like, yeah, you are. And now if she says, well, it's tough, you get 80, that's now a different argument, right? But ask. What she may very well be doing is looking at a minute per time calculation and say, of those 70 questions, like this is how I would do it, I would expect you can reasonably answer 60. So I'll give you a 70 question exam, but I will grade it out of 60, not out of 70. Simple things. Right? You don't know what that target is until you talk to your instructor. So you have to ask Miss Grace. Does that make sense? Right. She's nice and all that, so she'll probably have that nice conversation with you, but let's just say for giggles, she's evil. She says, no. Deal with it. What do you do? It's a hard one. But we're trying to address strategies for dealing with academia.
There's always a chemistry department.
There's always someone higher. That doesn't mean that someone higher is going to listen, right? But that's when you start filing grievances, okay? And you go up to someone higher and you say, hey, I don't think this is appropriate, what's going on with this? And if she's doing it, if that instructor is doing it consistently to everybody, it may suck, but it sucks fairly, right? And so it may not go anywhere, but it definitely doesn't go anywhere if you don't ask and if you don't challenge. Does that make sense? Right? And if anybody asks, who told you that you should challenge your instructor? don't say me. Okay? Kind of makes sense? Especially that last one. Questions? Okay. Oh, it's recorded, so that's lovely. I always forget about that. Theoretically, I wouldn't be tethered, but unfortunately I am because I didn't charge it. What I'm going to pass around now is the kind of attendance sheet. Just go ahead and write your name on it. And I will pass around worksheets for today. And so what we will do is go through kind of the first parts, just kind of general content stuff, and then practice questions that we can kind of work together as a class. I will also note, for those people that wanted the lecture recording, I'll put the YouTube channel up on the board a little bit later here when I get a second. But that's where I'll post it, hopefully later today. It is a live recording, which means as I'm passing things out, number one, I'm not very close to the microphone, and number two, well, actually not number two, there's kind of a dead white space. Okay, you just kind of have to deal with that. Okay. But as you're all used to, I'm sure, from online classes and watching videos, you just double speed and don't worry about it, right? Okay. Cool. So, let's see if we can work through this. Give me camera. What we're going to talk about today, for better or worse, is probably my least favorite section, which is gases, because I think there's a bunch of stuff that just doesn't need to be addressed. Okay, that is kind of small, but you've got the worksheet, so you should be able to follow along within it. When we talk about gases, they're a new kind of phase for us. We talked a little bit about solids, but most of the things that you've dealt with have been in solution. Why would we task you with working with solids and liquids and not gases? Any ideas? Why the difference? Why solids and liquids are things that we allow you to work with? Think into lab. When you go into lab, most of the time, what are you working with? Solids and liquids. We don't ask you to work with gases. Why not? Gases fill their volume. So we look back to their general properties of solids, liquids, and gases just go pretty much everywhere. So they're very hard to contain. Okay? On top of which, let's say we're working with a gas and they're hard to contain, they move up into the air and ultimately then into our lungs. So there's a safety potential hazard going with that. That can be dangerous, so we tend to limit that and remove gases from our overall lab curriculum. We do play around with them a little bit when we can control some of those spaces, as you guys did this week. All right? So the new thing that comes up with gases, as they fill that volume, what they end up doing is impacting the container they're in. So if we look at a balloon, we blew gas into the balloon, what happens? The balloon. Why does the balloon expand? Why? The room didn't expand. Why is the balloon expanding?
It's elastic.
Why is it elastic mattering? Well, if I just take the balloon, it's still elastic, and I just flap it around. It's not expanding then. Why does it expand when I blow air into it?
Gas pressure.
Each of those particles that I breathe in, those gas particles, are impacting the sides of the balloon. Okay? When it's not inflated, when we just flap it around, there's still gas particles impacting the sides of the balloon, right? Right? But there's not enough impacts, which means the balloon doesn't expand. It's only when I breathe in enough gas into it that we increase the amount of impacts. Those impacts now expand the size of the balloon. Right? So there's an impact per area that causes the change in the size of our balloon. Okay? That's where we're looking at pressure. right? So she's talking about pressure here is our force per area, right? We can increase the force in a variety of ways. One of the easiest ways is to put more stuff in. More particles means more impacts, okay? And that can increase our pressure. But it turns out there's a variety of other things that can also factor into it. And that's where she's listed some of these other principles. Volume, which we already saw when we blew into the balloon, what happened to the balloon? It got bigger, which means the volume of the balloon changed as well. Okay? And then we have temperature. How does temperature have an effect?
It expands the gas when it's hot.
Right? What happens if we heat up just a balloon? It does pop. Like if you had a sealed balloon and you started to heat it, you might just start to see, I had an old school fireplace, you used to go into the fireplace and you could see that part of the balloon expand, right? Because you're changing the temperature and doing some other things, but it's increasing the pressure within, right? We can take advantage of those different principles with our gases to manipulate different systems and do cool things, hot air balloons, right? We can liquefy gases by changing the pressure. Okay, so we can play around with those variables and the amounts to do some kind of fun stuff with gases. STP is a term that you'll see come up. It's one I will try my best to not rant about too much, but to be honest, I will. You're just responsible for knowing what STP means, and it is standard temperature and pressure. What is standard?
Sea level?
Standard means sea level, so if I have a standard ruler that's at sea level, what does standard mean? It's just an accepted thing. Everybody agrees that this is the standard, so we accept that measurement. So when we say standard temperature, we're now saying we have an accepted temperature. What do you think would be a good accepted temperature? Room temperature, why?
Because usually you don't have to do much to get it to room temperature.
You don't have to do much to get our room to room temperature? What is room temperature? That's an interesting question. What is room temperature? Okay, so we can use Fahrenheit, that's a fun one. So we'll accept 77. Okay, so we don't have to do much to get this room to 77. Oh, in the desert we do. We have to do a whole lot to get the temperature to 77. Okay? It's 100 degrees outside. We have to cool the room down significantly. There's a lot of energy that goes into it. Okay? So that's not what defines the standard. When do you think you're going to be doing your experiment?
We're in a lab.
When you're in a lab. So when you're inside. So it's not that we have to do less to get there. It's where are we going to do our experiment? We will likely do our experiment inside, not outside, because outside is really freaking hot. I don't want to be out there. So we'll create a standard of where we're going to exist. Okay? So yeah, we'll deal with that. So we could say room temperature. We said 77 degrees. What did you say? Fahrenheit? Fahrenheit's the word. Right? Is that our accepted science unit for temperature? No. What's our accepted science temperature? Celsius. How do you convert between Fahrenheit and Celsius?
Celsius. It's like
273 K sounds phenomenal. Does Fahrenheit begin with K?
No.
Does Celsius begin with K?
But Kelvin.
Ah, Kelvin. So there's another temperature. We get 3 different temperature units that we have to manipulate and understand and how to move between. Fahrenheit, Celsius, and Kelvin. Fahrenheit to Celsius is one that, I should cover up the microphone, is a generally important one. It's also one that I don't feel is particularly useful because it's just a formula. You memorize a formula and you solve it. You just plug numbers in. So is that something that's particularly useful for your life moving forward? Probably not, which is why we typically don't test on it as a competency. Okay? For an exam question in that unit, that makes sense. Okay? So we got Fahrenheit, we got Celsius, and we also have this thing now of Kelvin. Right? It turns out when we go to gases, we don't use Fahrenheit because America is bad. No, it's not that. Right? There's actually a different reason behind it. We also don't use Celsius. Celsius gets rid of the American equation, but we still don't use it. So how are Fahrenheit and Celsius different from Kelvin?
Kelvin's absolute.
Yeah, isn't it 0 Kelvin absolute zero?
Why do I care about absolute? What is absolute? Why do I care? Because I can get to that, or I can't get to that, but we can convert 0 Kelvin into Celsius and to Fahrenheit. Why don't I use Fahrenheit and Celsius? You just gave me a point, 0. 0 in Kelvin, I can get those numbers for Celsius and Fahrenheit. What's the difference between Celsius and Fahrenheit and Kelvin?
Is there decimals in Kelvin?
Yep, they both have decimals. The answer we would have a hard time with in this state because we don't typically get that cold. What do both Fahrenheit and Celsius do? Pick a temperature.
77.
77. Go lower.
20.
Thank you. We're hoping there wasn't a 76. Go lower.
0.
0. Go lower.
-100.
Negative 100. Do that for Fahrenheit or for Kelvin. 173. Go lower. 0. Go lower.
-100.
No. You can't go lower for Kelvin. Kelvin is only 0 to positives. You don't get a negative value. And what we'll find is that when we manipulate gases, we need positive values for all of our temperatures. We can't do calculations easily with the negative numbers. Okay? Those negative numbers mess with the relationships and they vastly complicate things. So the Kelvin scale helps to simplify that system because there's now an absolute limit on that low end and it's still a positive value. Arguably it's not positive, but whatever. Okay? It's not negative. It's the big deal. Okay? So our Kelvin is 273. How did we convert Kelvin? What was your?
Oh, I said you add or subtract 273.
You add or subtract 273. Okay, so if I have 273 Kelvin, what is it in degrees Celsius? Do I add or subtract? In this case, I'll subtract. So it's deciding where we're going, which means 273 Kelvin is what degrees Celsius? 0. What is room temperature in degrees Celsius? I don't know, that's a BS unit. I don't want to use that. You all look at the thermometer when you get in the lab every so often, see what temperature read? There was a lab you were supposed to do that, right? Read the temperature? Yeah, it's like 22. Where's 0? That is freezing, not just figuratively, oh God, it's cold in lab. No, that is literally ice changing state. The standard temperature is 0 degrees Celsius. When are you ever going to be in a lab that is 0 degrees Celsius? You won't. We accepted as a standard something that doesn't exist for us. That's a pretty stupid system to use. Which is why engineers went like, that's a stupid system to use, and they picked 22 degrees Celsius. So if you get an engineer talking to a chemist using gas stuff, guess what happens? They get different numbers. They're like, what the? Why are these numbers not matching? Because somebody picked a reasonable standard temperature and somebody picked a stupid standard temperature. Right? So standard is not standard. Depending on what you're trying to do, you get different systems out of it. Right? And that messes with all the calculations behind it. Right? Pressure is the other accepted thing. There are units for pressure. She's got a bunch of conversions, I thought, at the top of that, but I must be remembering a different part of the worksheet. There's different units for pressure. Why would there be different units for pressure? Why are there different units for temperature? Location. So it's only useful to use Fahrenheit in one place. When you move it to a different place, it's no longer useful to use Fahrenheit. Why do we have multiple temperatures?
We're more useful in different circumstances.
Fahrenheit versus Celsius, I would argue, are pretty much the exact same system. Why is it called Fahrenheit? for the scientists that defined it? Why is it called Celsius?
Scientists of the planet.
For the scientists that defined it. Why do we have to use both of them? Because both of them built up enough of a following of people using that measurement system that they yelled at each other, and we just now have to deal with it. Guess what happens with pressure? Pressure is the observation of what gas is doing. That's a really easy thing to observe. So guess what? We get tons of pressure units. PSI, atmospheres. PSI, pounds per square inch. See that in your car tires? Right? Atmospheres. Oh, sweet mother, what are we doing?
There's some, like, this, a block broke, I mean, I can't.
Okay. Are we
Oh my goodness.
just a cricket?
Yeah.
Okay. I've seen scorpions, and I would have jumped too. So, our
That's what sound.
Let someone pass that.
So pressure gets different units because we get lots of different people measuring it, and there's different systems that we want to look at. Which means if they're different units, what do you potentially have to do? Convert between them all. Right? Those conversions, you'll be given conversion factors to make those conversions, at least as far as Chem 130 goes, and I believe as far as your class goes. You will not be expected to memorize any of those conversions. You're just expected to use them. Okay? Cool. So we got all our basic tenets now behind it, and now we move into all these famous people who have defined some of these relationships. So again, old science, lots of people made observations. In those observations, they got to stake a claim and attach their name to it. So we encounter something called Boyle's Law, because a man named Boyle discovered it, right, and defined it, and then that, to give credit where sort of credit is due, we now recognize that name associated with it. Different instructors hold different weights behind names associated with formulas, so be aware of that. You may be asked, what is Boyle's Law? What is Gay-Lussac's law? What is Charles's law? You may be asked for that, or you may be asked to manipulate what the law means. Okay? So when we look at Boyle's law, officially what he noticed is that if you multiplied the pressure and the volume for one condition and the pressure and the volume for another condition, that when you multiplied them, they equaled each other. That's weird. Why would they equal each other? That's kind of interesting and bizarre. So we've got this equality, and this creates now a relationship. So what she's asking for here is now for you to define that relationship between pressure and volume. Does that equality, P1 V1 equals P2 V2, define a relationship between pressure and volume? Do you see pressure? What is the symbol for pressure? Take a guess. P, cool. So we're all on the same page. Pressure begins with P. Our symbol for pressure is P. Does that equation provide a relationship between pressure and volume? Yeah. Okay. I would argue yes, it does. Okay. But it's not a clean observation. We've got mixed units on each side. So what we're being asked to do here is to separate like terms. Put pressure on one side of the equality, put volume on the other side of the equality. So do it. What do you have to do algebraically to get pressure all by itself and volume all by itself? Ask your partner. Okay, so what happens if we get try and do this. So I heard a suggestion, get volume to the other side. So I'm going to subtract minus volume 1, subtract volume 1, and I get P1 equals P2 V2 minus V1, right? Okay, there's some no's. I appreciate the no's. Why is that no? Yeah, we can't just decide to move things based off of whatever operator we want. That's a multiplication system behind them. We have to divide both sides, not subtract. Okay? What happens to the left-hand side of the equation? Well, if I divide V1 by V1, what happens?
Cancel each other out.
They cancel each other out, which means on the left-hand side of the equation, what do I have?
P1.
P1. What happens on the right-hand side of the equation?
P2, V1, or P2.
I get P2, I get V2, and then I would have divided by V1. Can the V1 cancel the V2? No, why not? They're not the same. One is P1, V1, one is V2. Those are different systems. They can't cancel perfectly. So this would now allow me to create a system where if I knew 3 of the variables, P2, V2, and V1, I could solve for P1. Okay, does that kind of make sense? Is this the expression that we're being asked for? Have we condensed all like terms? No. On the right-hand side, I have P and V. So what do I need to do? Divide both sides by P2. Now what do I get?
P1 divided by P2. P2 divided by
That's the expression I believe we're looking for. So all we're trying to do is see the different relationships between those. That's it. Okay? Which of those relationships do we want to manipulate and use? It depends on the system that you're working within. Okay? But what we're trying to do is combine those like terms and recognize those patterns and see how they're related to each other. One thing that can help us see that relationship, let's just look at P1 and V1. Where are they across the equation? Where are those? One's on top and one's on bottom. We could reference them as inversely positioned, which means the relationship between our pressure and volume is inverse. Okay? When pressure goes up, what must the volume do? What's the inverse of up?
Down.
Down. Okay? That allows us to manipulate that system, and we can then run calculations or just do thought experiments like we just did. What happens when one goes up, the other must go down to counteract it. Kind of make sense? So what happens with 2? That was not the right button. Undo. Yes. Sometimes life works for you. So what happens with number 2? Same deal. Work it out with people around you. And I'll rewrite the expressions. So what do we notice?
Need to multiply.
We have to multiply both sides, okay, by depending on what we're looking at. And if you're saying multiply, you're probably multiplying by one of the temperatures. You're probably trying to get T1 to the right. So you multiply both sides by T1. The expression we could get out of that would be P1 equals P2 over T2 times, where'd it go? T1, right? That would be similar to what we had up here, a useful expression to solve for our starting pressure if we knew all of those variables, right? If we're trying to get those like terms grouped with each other, we could set up that or relationship again. Pressure 1 over pressure 2 equals temperature 1 over temperature 2. Yeah? Comfortable enough with the algebra? Okay. Now let's look at the relationship. If pressure 1 goes up, what happens with our temperatures? It will also go up. They're directly related. We can see those relationships a little bit cleaner and better when we establish those lines. Okay. Charles goes through and does the same thing. So we can do more fun stuff with all this P1, V1 stuff. Why do we need all the ones? What's the point of all those ones and twos? Whoops. They're different values. They're different values or different measurements for different systems. It's the same measurement done at a different time in space. So it's a slightly different relationship, which is why we need a new variable to represent it. Okay? We don't want to create a whole brand new variable out of nothing because we don't want to lose the meaning of T being temperature. Kind of make sense? Okay? So we get all of these relationships, and those are all cool and neat and fun and grand, but to me, ultimately, all those really do is build up into one big conclusion. I did it again. Whoops. Oh, nope, I didn't need to do that. One big conclusion, which is now at the bottom of our page. Someone took all of that information into one system and a little bit more, because we see PV, and we see our T, we're adding an N. What is N?
Arbitrary.
What unit is an arbitrary number? It's not just an arbitrary number. There's actually a unit associated with it. It's a measurement. Do we have a unit that describes the number of something? Moles. Yeah. N is for moles, not because moles starts with N. It's because what does moles measure? It's a number of particles. That's why we're getting the N from. So what someone was able to do is that they noticed if you arranged all of these equations, we could get this special response, that PV equals nRT. And R is the last kind of interesting piece within this. P, we said, was pressure. V is our volume. N, we said, was moles. And then we get this weird R thing, which we'll come back to in a second. And T for temperature. Temperature is too long of a word. All right? Then if we take those things that we know how to measure, pressure, volume, moles, and temperature, and we collect all of those terms into one space. Okay? So we're going to end up doing that division process. Moles are going to now be on the bottom. Temperature will also be on the bottom for us. And what we'd be left with is all of those together equals R. Well, what is R? R is a constant. For any system in gas, when we measure the pressure, the volume, temperature, and the moles, and we use this mathematical equation, it doesn't matter the gas, it doesn't matter the pressures, volumes, temperatures, or moles. When we put them into this relationship, they always equal the exact same number. That number is R. Like R is not a number, right? That thought crossed your brain, at least a little bit. R is not a number. So we didn't define what the R was. But if we go through and set that up, we find out that that R has a couple different values depending on the unit system we're working with. What units do you measure pressure in? ATM, which of these two numbers has ATM associated with it?
Second.
The second one, so there's ATM. Volume. How do we measure volume?
Liters?
There's our liters. Notice pressure and volume are located where in our relationship? In the numerator. Where's the liters in atmospheres?
Numerator.
In the numerator, the slash is what denotes that difference between numerator and denominator. We're going to come back to that because it's an annoying format. Right? Units on moles. Stupid question. It's moles. There it is. Units on temperature.
Kelvin.
Kelvin. Remember we talked about temperature, right? We said we only had to use Kelvin. We couldn't use Fahrenheit. We couldn't use Celsius. Why not? What happens to this relationship if you use Fahrenheit? I could get a negative temperature value. So if the temperature was positive, I'd get a positive R. If it was negative, I would get a negative R. Is that constant if I move between positive and negative? No, there's the issue. Right? So if we measure a temperature on an absolute system, this is where absolute zero is coming from, right? I don't have to worry about that negatives, and I get a standard constant all the way through. Pretty neat observation. Right? The other unit system given here is kilopascals, probably because Ms. Grace is more engineering bent, and they tend to use pascals more often. Right? Atmosphere tends to be the chemist one. Why do chemists pick atmospheres? Where's our standard atmosphere number? 1. Whereas our kilopascals, I don't even know, but it's not 1. 101? Yeah. 101 point something something somehow. That's too many numbers. 1 atmosphere makes our life easy. Kind of, sort of? So when we're talking about gases, it's now just how do we manipulate all of this information and just plug and chug our way through? Right? There's a couple more facts on the back. And I'm going to bring in our ideal gas law with the last one. Let's try that. Where'd it go? So, we get one more fun law. Dalton's law of partial pressures. This is, calling it an artifact is a bit of a stretch, but when we talk about gases, they can be very, very complex. So what we do is make some assumptions, and we call them ideal. Ideal gases function with certain things. Okay? Some of those big tenets, you get elastic collisions. You can't take a gas particle and then smash and they stick. That's not ideal. Because how much do they stick? Do they stick perfectly? Do they stick imperfectly? So instead what we say is they just bounce. Boop. Zero interaction, or minimal interaction. Right? The other big one is the volume of the particle. When you came into this room, where could you sit? Anywhere. Really? Who said anywhere? Were you the first one in this room? It doesn't matter.
No.
No, you were not the first one. Okay, who was the first one in this room? You were. You could sit anywhere. You think you could sit in his chair? Okay? That's going to be hard. Right? As soon as you walk in, you don't have, or because he's already here, you don't have the same volume accessible because he's already occupying. Okay? That's the reality. With gases, we say they don't have a volume. What does that mean? If he's a gas, guess where you can sit? Exactly where he's sitting. Because you don't have a volume. Which means the more particles you put in, what happens to the overall volume? Stays constant. It doesn't change. Right? That's not the reality of our world. But when we look at gases, because of the properties of gases, they're so low density that as an estimate, works out pretty well. We just have to get small enough to make that true. When we do that, certain things become valid. The ideal gas law becomes valid. All of those other laws become valid. And this other one's, Dalton's law, becomes valid. Right? And all Dalton's law says is that the total pressure in the room is due to each of the different particles that are there. It doesn't matter what those particles are. Because they all have the same properties. Right? They don't have a volume. They don't occupy any of that space, which means you can take the pressure of gas 1 and the pressure of gas 2, and when you add them together, you now get the total pressure. That's it. Really, that's it. You just add them up. Right? The last one is Avogadro's hypothesis. This is the big rant. Okay? If we take an equal volume of gas, an equal amount of moles, it doesn't really matter which one, what we'll notice is we get this ratio that comes out of it. If I take a mole of any gas, okay, let's pick hydrogen gas. Okay, hydrogen. Formula for hydrogen. Hydrogen gas.
H2.
H2 is one of those diatomic particles. Okay? Has a mass of about 2, right? Because there's 2 particles. And I take the mass of, let's go iodine gas. Iodine, still I2, diatomic. Iodine lower right, it's 127. 127 times 2 is 54. Thank you. No, it's exactly remind me here. 254. Right? And I take those gases. They both equally contribute to the pressure of the system. Even though iodine is massively larger, right? That larger is assuming this volume thing. But ideal gases, what do we say? They all have the same volume. It doesn't matter their mass. Right? And that simplifies our calculations vastly. That's what allows us to do really neat things like this, which is add up the pressures. Right? We move to Avogadro's hypothesis because of this. The volume occupied is going to be the same. Right? In this case, we're saying 22.4. Right? We did lab today. Wednesday did lab on Wednesday. That was a clearly obvious statement. Right? Did lab on Wednesday. Was it 22.4? No, it was some other number, right? 24.5? Yeah, 24. Why is the number changing? Right? Well, this number is dictated based off of PV equals nRT. When we go through and say 1 mole of gas is 22.4 liters, what have we defined? We defined N as moles to be 1 mole. We defined volume to be 22.4 liters. Okay. We clean up our equation, PV NT equals R. It doesn't matter the gases, this expression must be true. It has to come out to be constant. If I've defined these as mole and volume, did I define pressure and temperature yet? No is a good answer, but if we rewind light years backward, we talked about a brief sequence of letters, STP, which was standard temperature and pressure. Have we defined temperature and pressure?
Technically,
Yes, we have. Okay, which means I also know T is, what did we say standard temperature was? Kelvin is the unit. What's the number?
So 273.
273.
1 atmosphere.
And I know my pressure. I was trying to be fancy and use different colors. 1 atmosphere. So what someone went through and did is said, okay, I want to know the relationship between moles and volume if I'm at this point. So what could we do? We could take temperature and pressure, we can plug it into our expression, knowing R from the previous page, and we just solve for the numeric relationship between volume and moles. Why would we want to do that? Because you get this neat thing at the end where you go, oh, look, it's the same. I can pick the same number. Cool. When can I pick the same number? When is this true? Okay, and we can write the expression that comes out of it. Okay, what we're saying at STP is 1 mole equals 22.4 liters. When is that true?
STP.
At STP is a really important statement. I'll accept that. might regret erasing that, but I did it anyway. If I have a 3 molar HCl solution, that's a Cl, not a U. What is the mole to liter relationship for this solution?
3 moles per liter.
3 moles is 1 liter. What if it's at STP? Still 3 moles per liter. Why is it not that? Why is this different than that? There's another condition. This one is 3 moles per liter. This is 22.4 liters is 1 mole. We're still at standard temperature and pressure.
Is it because the other one's liquid?
There it is. This red thing is technically a solution, right? A mixture, an aqueous mixture. The black one, the one we're talking about here, isn't for mixtures. It isn't for solutions. It's for gases, and gases only. This becomes a large sticking point, is that we go, oh, I've got this number that is always true. It's not always true. It's true when I'm looking at a gas and when I'm at standard temperature and pressure. Those are 2 very important caveats behind that conversion factor that you have to be very careful of. The one that gets tested on is gas, because we'll ask you to do conversions between moles and liters for a liquid or for a solution, and you start using 22.4 liters. Right? That's only true if it's a gas. How do you know it's a gas? How do you know we've been talking about gases at all today? It's a very silly question with a very easy answer. How do you know we've been talking about gases today?
Because it says that.
It says, okay, I'm an it now. We're talking about gases. We use the word gas. How do you know you're looking at a gas? When you read the question, does it say gas? Yes, that's a very good clue that you should be looking at gases. This could be a useful conversion factor to use. Right? What other thing do you need to look for?
Measurement.
STP. STP should be the other signifier. If you move into Chem 151, more general chemistry, they will probably test you more on this STP side. Are you reading the question to recognize that you're at standard temperature and pressure? Right? If you are, good. Chem 130, we tend to focus on this gas one. Do you understand that this conversion factor is only valid for the gas phase? If you know that, you're good. Right? Typically. It is rare to throw in the STP conversion factor in students. Kind of make sense? Okay. Which sets us up with what? You got questions? Is it all easy?
What is 1 atmosphere like pressure? How's that measured?
How you measure pressure is a force against a surface area. Right?
It's just
So what we went through and defined, typically pressure was measured, I believe, initially off of centimeters of mercury. So you took a tube, let's not go upside down. So you take a tube, that's a tube, okay, and you fill it with mercury. When you turn it upside down, what does the mercury do? It falls out. Like, I take a tube, I took a soda bottle, and I turned it upside down, all the water runs out of it. But instead of just doing that, I put it in a container with a liquid underneath. Does the liquid all run out? No. Some of it stays trapped inside that tube. Okay? And so what we end up seeing is that gap. Why did the liquid not run all the way out now?
Is it pressure?
What pressure?
The pressure that was created between the water or the liquid and the other liquid.
No. What are we talking about today? Gases. So if you say the pressure between a liquid and a liquid, why would we talk about liquids if we're talking about gases? Where's the gas pressure?
Between liquid and gas.
It's here. That gas is pushing down on this liquid. Right? For this liquid to come down out of that tube, what has to happen to the outside?
Raise
It has to rise up. Why is it not rising up?
it. Pressure.
The air is pushing down on it. Right? That's what keeps the liquid in the tube. So when we talk about one of our initial stages for measuring pressure and gas pressure, we use it kind of with weather. Okay? You hear people, oh, we have a high pressure system, low pressure system, we're talking about weather. This is ultimately what they're talking about. How is that air pushing down on that tube? Well, how would I quantify this? What happens if this air pushes less hard?
And mercury would mix and fall down.
This liquid drops. So I could go through and say, oh, this is a high pressure system. And if it's a high pressure system, the liquid goes up. So I could talk about the height of the liquid in the tube referencing my air pressure. Okay? That height, typically centimeters, and we need a liquid. Well, what liquid should we use? What happens if I leave a cup of water on the counter? It does nothing. Really, if we left a cup of water here on the counter and we came back in 2 weeks, you still expect, let's assume nobody drinks it or knocks it over.
Evaporate.
It evaporates. It transitions from the liquid to the gas phase, right? Which means if I'm trying to measure pressure, if the liquid starts evaporating off, what happens? That tube starts dropping. I need a tube filled with a liquid that does not evaporate. Right? So water's a bad choice. Gasoline, worst choice. Mercury turns out to be a really good one. Right? What's the problem with mercury? It's very, very toxic, which is why it's disappeared. But if you think about thermometers, you typically, or you may have heard of mercury being in thermometers because it's very good at measuring our pressure differentials, okay, and temperature and other things, right? But it's very, very toxic, so we limit our exposure to that. So our initial measurements were how much liquid was in that tube, and the liquid was typically mercury, and we'd represent it by the height, centimeters or millimeters of mercury, right? And then we could convert that into different systems. We could look at pounds per square inch. We could look at kilopascals. And ultimately, all they are is different ways of measuring that external force, okay, per a given area. Right? Why did we pick atmospheres? We picked atmospheres, again, because it just converted the numbers down to a system that was easier to manipulate. What's standard pressure for mercury? 760 millimeters mercury? I don't want to know that. I'm sure you don't want to know that either. Right? So we picked something that was a little bit easier of a unit system. How did we convert it? We just created a unit. Like, you can do that? That's how all units are made. I don't like that unit, so I'm going to create centimeters. I don't like that unit, so I'm going to create inches. They're completely arbitrary systems. As long as everybody agrees, they're valid. Okay? Kind of make sense? Okay. Which sets us up with the flip. We look at the flip, we've got a bunch of questions. Does she just work through questions with you, or does she leave you to play with them? Both. Okay. So, do you want time to play first on your own?
No.
Let's see. Can we see? I'll leave you to play with the first two. I'll give you first two conversions, just the top, just changing the following units. Set up a unit conversion process. A few questions on here. So it means you just didn't listen to me at all. Everybody sign in? So let's go ahead and do that very first one, tiny up at the top. It is very common. I've seen students just go, oh, I just multiply or divide. The problem with that is I just multiply or divide. Which one are you supposed to do? Right? All too common, we go, oh, it was easy, I just multiplied. And I go, okay, we move to a new question and say, oh, I just multiplied. No, now you're supposed to divide. So deciding whether you're supposed to multiply or divide in your conversion factors comes from your unit analysis, okay? Which means setting up an awful dimensional analysis system. But that dimensional analysis system will always ensure that you have the units aligned in the proper configuration to allow you to correctly solve a question. The faster and more efficient you become with that process, the more likely you can skip steps and not get penalized because you made a simple mistake. So if you're one of those people that you're like, I'm just confused with that process, don't just multiply and divide, write it out. Okay, that write out process, what do I want? Well, in that first question, it's kind of not super obvious because it's not listed as a question. What we're being asked to do is convert 359 kilopascals into atmospheres. Atmospheres is my answer. That's my goal, atmospheres. I said it in lab, but we'll say it for everybody that wasn't in lab today. Okay? Why are you taking this class? It's a prerequisite. You have a goal in mind. I would bet at best we get one student out of all chemistry that just takes a chemistry class for the giggle of it. Yeah, let's just take it. I don't care. Okay, that doesn't happen. Okay? We have a goal in mind, which means when you go through to solve a problem, you need to know what the goal is. Identify the goal first. Don't start taking numbers that you're given and mashing them together because that's where you run into problems. Right? My goal is I want atmospheres. Well, what do I want to start, or what am I given to start with? And everybody says this is okay. Maybe I heard a different answer over here. Okay? Most people go, oh, it's 300, and I'm going to say no. You're like, but it's 300. No, that's not the relevant thing. What's the relevant thing? The kilopascals. I don't care what the number is. What I care about is the unit, because the unit's going to help me dictate how I solve the process. Okay? So I'm going to start with that unit. I'm going to start with it over here. Okay? But I've got conversions, which means I have a numerator and a denominator. Where should I place kilopascals?
On the bottom,
Why do I want to place it on the bottom?
because you're going to a smaller number.
Okay? Smaller numbers are fine to discuss. One of the issues with smaller numbers is it is only a smaller number because you know something about it. You've known something about that process. Right? That becomes a challenging thing to manipulate and understand and follow and move through. Right? But let's work with it. We want kilopascals on the bottom. Okay, so we'll say 359, right? Okay, that was the given information, which means what shows up on top? 1. That's it. Because it's not 359 kilopascals related to anything else, it's only related to 1. So what do I need to do in the next step? Those two are not equal, so I have to do something to this. I have to do a conversion. In that conversion, what do I want to have happen? I don't want kilopascals. Well, where are kilopascals right now? On the bottom. So to cancel them, where do they need to appear in my blue step? Is this going to cause a problem? Anybody see it yet? You laughed, so I'm going to say yes, you just saw it. Okay. What do I want to convert kilopascals to? Atmosphere, that's my goal. I want to go to ATMs. So I will place them in the opposite location. I can put in numbers. We don't need to worry about numbers yet. What happens with the units? The kilopascals canceled. Did I want them to cancel? Yes, we're good. And I'm left with atmospheres. Yes, we're good. Where am I left with atmospheres? On the bottom. Where did I want it? What does that mean about my initial placement of the kilopascals in black? I placed it incorrectly. Okay? How do I know where I should place it? That is a very challenging question. What I would argue we should do is ask ourselves a slightly different question. What is kilopascals a measure of? Pressure. What is atmospheres a measure of? Pressure. Where do I want my pressure unit in my answer? On top or on bottom? On top. So where should it be on the left side of the arrow? Try it this way. Here's a 2. Where do I need to place the 2 on the left-hand side of my equals so that that expression is true? Atmospheres measures pressure. Where should my pressure unit show up on the left-hand side of the answer? On the top. It shows up in the exact same location so that it matches 2 equals 2. Okay? For those people being, well, I was flipped. What you're doing is cross multiplication. Cross multiplication is okay to solve one conversion. How often are you asked to do a single conversion? Think back to all the conversions you've done this semester. Fairly rarely. You've got to do stacked conversions. And if you're going to stack conversions, you need a slightly different process, or you've memorized how you do each and every single one of those conversion processes. If we align our units according to our systems here, we can now say 359 kilopascals over 1. That's the given piece of information in black. That was it. Those sides of the equality are not equal to each other. So what must happen? What has to happen? Conversion. Yes, I need to do a conversion in blue. In that blue thing, what do I know needs to happen? What has to happen to the unit of kilopascals? It must cancel. So where does it need to appear? What do I want to convert those kilopascals to? Atmospheres. Now if we look at the unit process, the kilopascals would cancel and I'd be left with atmospheres. What numbers should I place in front of atmosphere?
1.
That's where you would look at the top of the page, and you could look here. There's a little I there, we'll ignore that. What number shows up in front of ATM? 1. So what shows up in front of ATM in my conversion? 1. What number shows up in front of kilopascals in my conversion factor? Do I multiply or divide? I divide. The conversion process aligns it and allows me to see exactly where to place those conversion factors and how to do the mathematics behind it. Kind of, sort of. We're stacking that process so that we could now run multiple conversions on top of this. That's the beauty of using dimensional analysis as opposed to cross multiplication stuff. Okay? We look at the degrees Celsius to Kelvin. How do we do that one?
Add 273.
You just add 273 to it, and that's it. I don't want to do that one any more detailed than that. Jerk. So question 1. We got a lot of information. This is almost always going to happen with our gas stoves. Because we're looking at multiple relationships, multiple pieces of information. So this is where, as you read, I would recommend you pull that information out. I have a gas sealed in a can. We could even draw it. Here's my can. Okay? It's my can. Okay? And it's a pressure of 3 atmospheres. I was just given some information. What was I given? I was given a pressure at some condition. It's the first one I see, so I'll call it P1 equals 3 atmospheres at 25 degrees Celsius. What is 25 degrees Celsius a measure of? Temperature. Again, this should be T1. Why do I have to match 1? I dictated pressure 1. Temperature is aligning with that same thing. This is 25 degrees Celsius. What did we say about the utility of degrees Celsius when we look at kelvins? At gases. Oh, that gave away an answer. How useful are degrees Celsius when we look at gases? Not. What do we want to do?
Add 273.
I would add 273 right away. 298. 298 Kelvin. If you write big, get a separate sheet of paper. Okay? As we continue to read, a warning on the can says the user should not place the can at a temperature that will exceed 52 degrees Celsius. What would the gas pressure be if the can was at 52 degrees Celsius? What is the number that we are given? We're actually given two pieces of more information. What's that information?
3 atmospheric pressure, 52 Celsius.
We're given a new temperature. I'll give you that. Temperature of 52 degrees Celsius. Immediately, what could we do?
Convert it to Kelvin.
Add our 273. I can't do that math. We're- People spitting out numbers. What was the number? 3 something?
325.
325 Kelvin. Was given another piece of information. What was that last piece of information?
The gas
3
pressure.
atmospheric pressure.
3 atmospheres we already have. That was P1. It's kind of a weird statement to say we were given another piece of information, but there's more information in the question that we have not translated on the page.
Oh, the standard is 1 atmospheric pressure.
No. What are you solving for?
The gas pressure at 52.
What was I given? P2 exists. Careful. P2 exists. Do I know it? No. That's the one I'm solving for. Okay? So now I have 4 pieces of information. I need a formula that would allow me to bring those 4 pieces of information into a way that would allow me to see P2. Make sense? So this is where you could flip to the front where we wrote out that relationship. I didn't write it on this sheet of paper, so I don't have it. I'll try and make it up as I go. What do we say for that? Said P1 equals P2 V2 over V1. That's what we said. But in this case, what did we want to solve for? P2. So what we could go through and do is change our numbers around and say we're solving for P2, which is P1 V1 over V2. Now what can I do? Do I know P1?
Yeah.
Do I know... Oh, I did V's. God. That's what happens when you look at the wrong formula. Where'd I go? Number 2. This was the expression that I believe we wrote down. P2, P1 times T1. What we want. Do we know all those systems? Do we know P1?
Yeah.
Yep. Do we know T1?
Yep.
Do we know T2?
Yeah.
We can now plug it in. Make sense? So all you're trying to do is read each of those questions, right, and establish what information is given. Almost all these gas law systems are just what is the information, now which formula just matches to the system. Right? I would argue you just use PV equals nRT, and you just manipulate that as you see fit. Okay? What do I mean by that? What did we say R was?
Constant.
Constant. So if I have PV equals nRT, I've got PV over NT equals R. Make those ones. I know that will also equal P2, V2, N2, T2. For this particular question, what happens to N1? What is N1? It's a hard question. What is N1?
That's the moles.
Moles. What were the moles for this question?
Didn't say. Unknown.
Okay, so that's hard. What is N2? Moles at condition 2, right? Doesn't say what that is either. Does it say it changed? No. So what is N1? You can could make it one and told me not gonna matter. It's the same thing as N2. They're the same on both sides. What happens when you condense those terms? They would cancel. So if you're not given that information, it's because it's held constant and it cancels out of the expression. Our pressure and our volume cancel out. We get the exact same expression that we'd ended with, or we started with the last time. So using PV equals nRT can allow you to do these calculations without having to memorize those relationships. If you just use PV equals nRT. Requires a little bit more algebra to get them, but I would argue that algebra is easier than memorizing multiple formulas. Do apologize, I have run long, that's typical. But I don't have anywhere else to be, so if you've got questions, you can stick around and ask questions. I don't know what she asks for the worksheets. Should have passed these out earlier. She does have some homework questions, so since you're already walking out the door, stop walking out the door. Make sure you get this so you at least have it. If you know the people that left, I will send Miss Grace a message that several people left before I stop talking. But if you can get them that worksheet, that would be appreciated. And then I will try and get the lecture recorded, or not recorded, posted.
I would just
See you, John. Yep, see you. Have a good weekend.
How many questions were left? Like, I'm pretty sure the bug wasn't the issue.
If I were teaching this, I'd probably go totally away from formulas. Except
Yeah.
for PV.
Yeah, that's the only one I want to speak.
I just teach the students the pressure, pressures, the temperature's going up. What's the pressure value? That's what I have to do is do a.
Yeah. I always stick with just PV equals nRT and say there's some named relationships that are out there. You can memorize them if you want. They're in the textbook. PV equals nRT is out there.
It's symbolic. Pressure's not temperature. Pressure has to go up. Well, I know it's got to get a little bit bigger, and it's that ratio.
That's where I said I was just kind of pseudo boxed into seeing her worksheet, trying to follow her worksheet. So. And yeah, even that I didn't do very well of. You as well. I just talked a bit too much.
You did a good job. You did a good job.
So I need to learn to not talk as much.
I would try it. There's a good model on that sign.
Yeah,
For
Fed's
this,
got one.
not having to do that and just symbolically do the relationship. Pressure goes up.
Which is really all we need. So it's not that that what she's got is